So hi again, thank you for the introduction. I'm Gianmarco Cordi. I'm actually a PhD student at Politecnico di Milano, Italy. And today I will talk about our experience importing a virtual screening application on a major supercomputing center in Europe, at least, on LUMI in particular. And during the presentation, I will say we, because I'm speaking on behalf of a joint effort, multiple teams from Politecnico di Milano, Università degli Studi di Salerno, which are two universities in Italy, and also from a point of view of pharmaceutical company, which is Dompe Farmaceutici. So also this presentation will be a study case, which in this case is a virtual screening application. I will talk about drug discovery, molecular docking, which is kind of similar to the name of molecular dynamics. We will see later on. And so I will briefly go through a bit of context, then we'll explain which were our challenges to using SYCL porting for the GPU part of our application, and I will show you some results we've got on LUMI. So to begin, this roughly pipeline described the drug discovery process, which is used to identify suitable candidates drugs against disease. And usually the process starts by identifying a protein which yield the disease in the end. So for example, for the COVID was the spike protein. And at the other side as input, you have this huge library space, chemical space of ligands, drugs, or compounds. And you have to basically understand which of them yields some effects on the protein. Which of them are more powerful, let me say, they are more effective against the protein, goes to other trials later on, in vitro, in vivo trials, and later on they get approved from some agency. We are mostly interested in the screening part. So since we have this huge library, I mean, trillion of drugs you could potentially have, we are interested in understand how we can improve this process using an in silico system. So basically in doing the simulation with computational method virtually. That's the case, for example, to doing screening using a virtual pipeline, so an in silico screening. The process involves evaluating each pair of ligands, drugs against a given protein, and to generate different conformation of these ligands and evaluate the interaction strengths between the two. Okay. It can be done in different way. In our case, we rely on a structural-based virtual screening that's called molecular docking, which basically look at a fixed instant in time and try to model the ligand position around the protein and doing different rotation and translation without considering time evolution, Newton's equation, and so on. It's more simple and thus faster. It allows to screen this huge library in a smaller amount of time. Once we have the ligands bound into the protein, we have to understand how to evaluate the interaction strength between the two, because maybe this kind of conformation is not feasible. It will not yield any kind of therapeutical effects. So what we use are called scoring function, not that a surprise, and that takes an input, the protein, and the conformation of the ligand they give out, and the output is a numerical value that you can use, for example, to rank among these conformation and decide which of them could go to later stages of the pipeline. There are different types that can be empirically based, physical based, machine learning, artificial intelligence, different way to do it. In our case, we rely on an empirical one. So basically you combine together different chemical interaction, hydrogen bonding, van der Waals forces, and you make a regression on them. Okay, that's a little bit of interview. Now, why we are talking here about SYCL and HPC. And as you can guess, this process is very computational intensive. Evaluate each pair of ligand proteins is a long process, but the good news is that it is an embarrassingly parallel problem. So they can be evaluated independently. And thus, we leverage the computational power offered by supercomputers to have dispose a lot of nodes to evaluate more ligands in a single run, thus increasing the probability of success of the whole drug discovery process. The study case I will talk about is LUMI-G. That's actually the application we are maintaining, which is a virtual screening application, which is also part of a drug discovery platform. And it has been built and written from scratch to hinge modern supercomputer power. In the context of previous pandemic and urgent computing scenario, it has been used to launch different virtual screening campaigns. So, for example, for Zika, it has been used in the ATAREX for Zika process, but only the CPU version. And then for the COVID, in the XCAD for COVID virtual screening, also on GPU. And actually, that's, as far as we know, the largest virtual screening campaign ever run. We screen almost 1 trillion of compounds in 60 hours on the Cineca Marconi 100. And after that, we started the development of a computer-aided drug discovery workflow supported on the Euro HPC supercomputers. But with the deployment of LUMI, we got some challenges because, as I said previously, we got only the CUDA version and the CPU one, and we needed another porting to support also AMD GPUs. LUMI is based on AMD MI250X. So most of the challenge after porting everything from the functional point of view, so the kernel comes from the GPU approach that we have in LUMI-G. The XCAD for COVID virtual screening campaign we had has been done in collaboration with NVIDIA. So we deployed a new version of the code, a new approach. We shifted from a latency-oriented approach to a batched one, in which we try to achieve a full GPU occupancy. This kind of approach is very efficient for our use case. So instead of having to screen ligand in a small amount of time, we screen a lot of them, but the number increases in the same time frame. This approach is efficient only if you are able to reach full speed. So you are screening a lot of this compound, and also if you are able to use efficiently the most rare resource that in our case for the kernel we had is the number of registers that are deployed for each sibling multiprocessor. To do that, we use a lot of template metaprogramming. So there are a lot of type template parameters that changes the kernel register pressure. That depends on the loop unrolling capability of the compiler. And the different kernel will be used, different kernel implementation will be used to compute different batches of ligands. And these batches can be tuned obviously based on the number of them. So how many of these batches you have and how many ligands you have per batch. This is done not at compile time. This is done at runtime based on the hardware we are using. So the register changes. Thus the dimension of batches will differ. So the previous version, the latency one, processed ligand in order regardless of their features. So as you can guess, bigger ligands will require a higher amount of time. The best approach instead, pack these ligands in batches, try to get in the same batches ligands with an expected similar execution time based on this input feature like the number of atoms or the number of table bonds that they have. So for example, for CUDA, the number L of ligands per batch is given by this formula. So basically you are taking the maximum number of active blocks you can have per streaming multiprocessor, which is B. You multiply that for the number of streaming multiprocessor you have times the ratio between the number of threads per block and the actual warp size. So basically that's you want to compute the number of warp scheduler you need to for computing a single block. Okay. And when we started the SYCL porting of the application, as I said, we ported from a functional point of view, so the kernel, but we were more interested in analyzing how the application behaves with this GPU batched approach and on a multi-GPU, multi-node architectures. So this is the translation we've got for the formula. We rely for SYCL on the kernel bundle API, so we get some knowledge about the workgroup size we can have for that kernel on that specific device. And in the end, okay, you can see that we got similar results. So on the y-axis and on the x-axis, basically we are increasing the number of clusters we can have. So for example, on the top rightmost part of the graph, you will have 23 times 6 cluster. So the more cluster you're able to do, the more number of batches you have, the higher the performance. In that case, on the top rightmost part of the graph of the table, you will get 2 times the original speed up of the application. And that's the same behavior, both for the CUDA implementation and the SYCL one. I'm referring on the one API version on A100 GPUs. And the same apply for the throughput of the application. As you can see, you have on the y-axis the number of drugs you are able to evaluate per second. And on the x-axis, you have the normalized bucket size. So that's the value L. You can see that there are peaks in performance in correspondence to this value. Obviously, you can use a multiple of this, reaching a maximum value based on the number of the available memory you have on your GPUs. But still, both the CUDA and the SYCL version show similar behavior for this batched approach. The point is, based on the throughput we got, we try to investigate why this happens, and this showed that the type template parameter had a huge impact on the register pressure, especially obviously if you increase the number of atoms, the loop or rolling capability of the compiler will reduce, so you will have a high register pressure. And still, the one API compiler in this case shows a higher usage in registers. This will limit the capacity of launching more blocks in parallel, more ligands, thus the reduced throughput you end up. So once we've got our results with NVIDIA GPUs, we started to get support on AMD one, so for AMD architectures. And that's happened on a benchmark access on LUMI-G, on the GPU partition of LUMI, but we still haven't any kind of reference. So on NVIDIA GPUs, we had the CUDA one, which was very efficient in our case. On AMD, we have nothing. So we performed a naive HEAPify porting using a Clang version that we have tested functionally, but not fine-tuned as the SYCL and CUDA implementation. So that's for the AMD support. So we reached out on LUMI, which is a supercomputer located in Finland at CSC data center. It's actually the 5th supercomputer in the world with 550 petaflops. And that actually is the most powerful supercomputer in Europe. And it's based on the HPA Cray architecture. Basically, for each computing node, you have 4 AMD MI 250X, which then they are divided into logical units. So in the end, you will end up with 8 logical GPU per nodes. Most of our time, unfortunately, has been spent trying to get a SYCL working toolchain because there were no official SYCL support, as the user support told us. And we had support with the installed GCC and LVM version, so we prefer to build everything from scratch to get a working SYCL toolchain, which was not easy because there was a lot of problem with older version of GCC and standard library and so on. In the end, that's the software stack we were able to get. So we used at least the recent version, more or less, of GCC and LVM. And this is also the version of the Adaptive CPP one API compiler we got. Also, the one API, we built it off from the GitHub repository. And there's also some hardware we use for reference. For example, for AMD GPUs, we use as a reference the AMD MI100 GPUs on E4 cluster. That's the result we got for our GPU, for our Legion application. On NVIDIA GPUs, using GPUs from Carolina supercomputer, NVIDIA A100, we can see that The adaptive CPP one API compiler perform basically similarly, but still the CUDA version with this batch approach is much faster. And that's, again, for the higher register pressure we've got that I will show you previously. But still, thanks to the SYCL porting, we are now able to launch our application on AMD GPUs on both the MI 250X and 250X, yeah, and MI 100. Here we get strange behavior because we didn't expect the adaptive CPP version to be that much faster with respect to the one API version. So we also tested it on MI 100 GPUs and we show similar behavior. And still also the heap version falls behind the adaptive CPP version, and we still haven't investigated that deeply. So also the scaling capability of the application remained the same. So we have been able to scale almost linearly on the number of nodes, which is no surprise. And also the multi-GPU support, after some tweaking, we have been able to get the almost linear speed up. So we have increased the number of GPU to 80. The speed up is almost the same. I think, yeah. Okay. That's to wrap up the conclusions. We have been able with SYCL to support other supercomputers in Europe. So we are now able to launch different of them. But there is still room for improvement because on NVIDIA GPUs, we still cannot go fully SYCL. There is the register pressure is too high. We still have to investigate why. But now still we have support for at least AMD GPUs, and we are also hopefully trying to test it on Intel GPUs. We are still investigating why we have this kind of different behavior between the two compilers and also to tune the heap version. Still, this is a benefit for future virtual screening campaign in urgent computing scenarios in case of, I hope not, other pandemics, for example. And that's it. Thank you for your attention. These are some acknowledgement for the grantee resources we've got, and that's the end of this presentation.
Forgive me if I missed this, but did you port your code by hand from CUDA to SYCL, or did you use Cyclomatic, or how did you derive the SYCL code?
By hand, the porting to SYCL.
Okay, thank you.
In terms of the higher register pressure that was seen in SYCL, was that observed in both adaptive CPP and DP? No, just one API. Okay.
Yeah, I mean, I also here for brevity, I put only the one API, but also for adaptive CPP, they are slightly smaller, the number of registers, but they are almost the same. Not that much of a difference.
Yeah, another question as well. When you're trying to build from source, what were the problems that you faced? And
No, it was not a problem of one API. It was a problem on LUMI because there were older version by the default installed. So the support was probably the default version of GCC was like 4 or 5. So when you try to compile, everything breaks up completely. And that's the problem. It's not a problem with one API. Supercomputer.
That's great. Thank you.
Hi. So the compiler versions for both one API and adaptive CPP were pretty old, especially in light of the fact that SYCL moves pretty quickly and things in the SYCL world move pretty quickly. So I wonder if you've had the chance to revisit the tests, perhaps on a local machine or so, where you can just quickly install a newer compiler and have some, like, does anything improve with newer compilers?
I haven't tried it yet, actually.
Okay.
But I mean, we are planning to get another access to, get the latest version of both adaptive CPP and one API, and it's something that we'll definitely do.
Right. Okay. Thanks.
So what do you view as the next steps? Are you looking to try to make SYCL have performance parity? Are you looking to move this code to use SYCL as a portability layer? What's the goal for you in the long term?
Actually, we are trying to at least make the SYCL version on NVIDIA GPUs compare the CUDA one. I mean, there are still, as I said, there's still room for improvement. I'm still trying to figure out if there is some problem with the generation of LDG instruction for custom memory. We rely a lot on that. So, I mean, Actually, right now, anytime I try to reach the parity between the CUDA and SYCL version, and then once we have achieved that, also on AMD GPUs, or still investigate why there is this difference, because also for the AMD MI 250X, I mean, if you look at the number of teraflops, they are almost 4 times the number of the A100, something like that. And if you look at this case, this is not the case. So, I mean, yeah, there's also the case on AMD. There is still work on that to do.
I got a question. So for MI 250X, do you happen to launch prime-sized work groups, or any like 2D, 3D work groups?
No, something that I haven't tried it.
Okay.
And probably I have.
Have you profiled the MI 250 runs for occupancy?
No, not yet.
Okay. Cool. Thank you.
So, because of the register pressure, so are you using the USM model or the buffer accessor model in your code?
USM.
Oh, okay. And you're still getting that much higher registers? Okay.
Yeah, I've seen that. I mean, there are some cases, there are some local accessors that I'm trying to remove, or at least try to use them in a different way. And I've been able to scratch some registers, like 10 registers. But I mean, there is still a high register pressure, and I'm trying to figure it out. What can be the reason?
Okay, thanks.
Are you using the kind of get linear ID, get this ID, get that ID member functions?
I don't recall it exactly. I can check after that.
Okay, thank you.